Hi, my name is Nate Elsop, and I'm going to discuss distinguishing, coloring, and automorphism. So to start, I'm going to start off with what the goal is. And last time I wrote everything out, but this time I think I'm going to type it out so it's a little bit neater, except for when we get to the graphs. All right. So basically, the goal for distinguishing, coloring and automorphism is to assign colors or labeling sorry about that. Labels, I mean, to the vertices of a graph so that it destroys all of the non-trivial symmetries, which is what I mean by symmetries. Symmetries. That can also mean automorphism, which is relating back to the topic. Of the graph. To put it in simpler terms, it just means to break, in quotation marks, symmetry. Oh, I keep on spelling stuff wrong. And be able to identify a vertex, you, my God. Uniquely by its graph properties and its color. So that's just basically the overall overarching goal and just the purpose of what we're talking about today is to assign labels to vertices on a graph to make sure that it destroys all the symmetry. Oh, my bad. Not just symmetry, non-trivial symmetry, which basically means, I'm just going to do a simple graph. So let's do this one. Bam. Let's do a cycle on phi of vertices. Oops, that's a bad way. Sorry, start showing off my bad drawing skills. Do that, and that. Okay. So a trick to this for doing this is that what we learned in class with being like, okay, so let's say I draw this vertex yellow and this one red. It can't, well, like what we learned in class is that adjacent vertices can't be the same color. So like this one to this one, it can't be yellow, but this to this is okay. Talking about this, what we're talking about today, that doesn't matter. Like we're throwing that out the window. It's totally okay to put colors next to colors via adjacency and all that. So let's say here, actually I want this one to be yellow. I'm just gonna color over. Yellow, and yellow. And let's just, maybe this one's 2. Let's just put red and red here. The thing is, it can't be red because if we look here, there's a symmetry that goes right there and it reflects. So the only way to make it non-trivial isomorphic is by making sure that one of these two red vertices is not red. And let's just change it to green. And now it's non-trivial isomorph. All right. Now going down to the history, basically this problem started off with someone called Frank Rubin. And instead of what the definition or the goal said, he translated the problem into keys and a loose string. So what that means is a key is a vertex, basically, and the loose string, oh, that's the strings, let's put that, are edges. And the basis of the problem is, let me just move that down. The basis of the problem is that you have a ring. Well, it's not strings. I guess more like a key ring. You have a ring of n keys for different doors. Each key opens a different door, and you're not able to tell the difference the keys. So the problem that you stated was, what's the fewest number of colors you need in order to color the handles of the keys in such a way that you can tell, you can uniquely identify each key. So that's how he stated the problem. And this was back in 1979. And this was just a general problem that he introduced. It was later brought up, was later reintroduced by Michael Albertson and Karen Collins, which was in 1996 that they brought this up, when they found, or more like when they provided a motivating example for Frank's problem. And I'll talk about what examples exactly when we get down to the examples part, which we're going to right now. So that's just the basic history of this problem that we have. So we're trying to identify via, well, more like in Frank's way, we're trying to identify which key is which by using the least amount of colors via keys. And if we're talking about with a graph, we're trying to figure out which vertices, how do we distinguish a vertice from one another? All right. So let's move into the examples. So the first example is asymmetric graphs. So let me just draw a random asymmetric graph. Let's do that. Put one down here. And do one right here, here, here. Connect them in a way. All righty. So just seeing on how this graph is not symmetrical at all. No way you can make it symmetric unless you add vertices. So like one like right here, if we connect that, but we're not going to. So basically, this, we're gonna call this G actually. This is G. So let's say, and when I'm gonna start like, oops, no, I want to write it up. I want to type it out, I mean. When I talk about dist G, I'm gonna mean, when I put G, I'm gonna put G for all the graphs that we do. So dist G is equal to 1. And what dist G means is fewest number of colors required such a coloring of G. That's supposed to be capitalized. So in asymmetric graphs, dist G, which is the fewest number for distinguishing, is 1. And this is because the graph is already not symmetric, which means no need to add more colors if all the vertices are already able to identify easily. Oops. All right, moving down to path graphs. So let me just draw a path graph. What do we got? I put down 5 in my example. Let's do that. So for this one, we're going to label these vertices and make it easier to explain. So 1, 2, 3, 4, 5. So the automorphic would be 1 can go to 5. So 1 to 5 can do it, and 2 to 3. So the only a way we can make this non-automorphic is by just making one vertex, one of the end vertexes, a different color from the rest. So let's make this one red. And that right away breaks all of these. Won't break these two, but group isomorphic. Not isomorphic, automorphism. Automorphism. Group automorphism will make it so that these colors stay the same. So, in general terms, dist G, and this is also call all sample graphs that I do. I'm gonna call them all G, except for when we get to cycles. Dist G is equal to, oops, 2. And this is because like I said before, we're trying to break the symmetry that we do. So easily symmetry, we could just split that right in half, and we can do symmetry right here. Ba, 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 if this was white. But if this is red, like it was before, now that symmetry can't be done. So we leave it as having two colors. Oops. All right, moving down to cycle graphs. That graph is unique. Well, actually, I forgot something in path graphs. This is only due if, and only if, n of the graph is, oops, greater than or equal to 2. Can't do the greater or an equal sign. I guess I could if I want to, but I'll just leave it like that. So this is only possible for a path graph if the number of vertices of the graph is greater than or equal to 2. All right, now moving down to cycle graphs. So just flip through my notes. Okay, so we're gonna do 2 different graphs. We'll start off with the first one being well, we already showed the 5 cycle up here that has to have 3. So let's do a 4 cycle. Bam, 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 and bam. All right, so that's a C4, and the way to color it is, let's do yellow up here, let's do green right here. Now, and let's do yellow again. Oops, well, I'm not sure why that's so thin. Okay. So yellow again, and I could make this yellow, but if I do that, sorry about that. Someone came into the room. Instead of a C4, we're going to do a C5 again to make it simpler and easier to explain. All right, bam, 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 and bam, bam, bam. All right, and my C5, and like I said before, let's color this one yellow. Let's do maybe this one red. Actually, no, not that one red. This one yellow, and this one yellow. Let's do this one red, and maybe I want to do, well, like I said before, this one can't be red because there's got to be symmetry across this yellow vertex. So this one has to be a different color. Let's do something like blue. So something like this only works in certain graphs. So, oops, not sure why it's so small. So dist of G is equal to 3 if and only if n equals 3, 4, and 5. So a C5 works. A C4, like I was gonna do, I'm not exactly sure how it's done, but in the references I have below, it will explain it in very much detail. So if you ever want to figure out exactly why, it's down there. And like shown, and doing it with the triangle, you can't do 2 because it'll be like that. Yeah. Alrighty. Also for cycle graphs, we're gonna do a C6. Let me draw a C6 real quick. two edges are kind of curvy, or three. All right, there's my C6. So the way to color it would be, let's make these two vertices red. We want to break symmetry. So obviously, 6, we can easily divide it across the middle. So we probably don't want to make this vertice red. Let's make this one red though. All right, and let's do our different color. Do blue. It's so narrow again. Okay. And our last vertice would be this one. So obviously, just shown here, no matter which way you try to make symmetry, this way, any other way, it won't make symmetry. So this means that the distinguishing number would only be, I'm going to call this one H. Distinguishing number of H would equal 2 if and only if n is equal or, well, no, not equal. Greater than or equal to 6. So the only way that a cycle graph can have a distinguishing number of 2 is only if the number of vertices on that cycle is greater than or equal to 6. And for cycles C3, C4, and C5, we'll have 3. And that's only for those cycles, not any other number larger. And we're going to talk about tree graphs now. So let's just draw a random tree that I have. All right, so there's my tree graph. Just a random tree graph. I'm not 1, 2, 3, 4, 5, 6, 7. This is T8 graph. So we're trying to do the same thing as usual. This graph, well, let me rephrase that. For tree graphs, it's similar to path graphs, saying like it's gonna be, well, let me actually just give you the answer in general, just right away, so then I can explain it afterwards. This is going to be called G again, is equal to 2, similar to path graphs. And what's unique, what's the difference between a path graph? Well, actually, I forgot to color in the last little tidbit that makes it different. Okay, and we're going to color that vertex. All right. Similar to path graphs, where usually it's like only 2. The distinguishing number is usually 2, and you would most likely only color the end vertices that are that. But with tree graphs, if the center of the graph is a vertex, and if there's no non-trivial isomorphism, so let me type that. If Also, let's say lefty center graph is not edge. So let me just erase something. Let's erase that. And let's just make this just like that. Maybe that can go like that. So now the center graph is just an edge, x, y. So what happens if the center graph is an edge? Well, then x and y have to be different colors. So y or x has to be at least, x has to be that one, or y has to be a different color from x. And this is only because, just disregarding this one because it doesn't have a non-trivial isomorphism. Oops. And has at most one non then x has to be one color and y has to be another color. Again, when I was reading through this in the paper, I was somewhat confused on like how they explained it, but I'll leave when I get down to the references, I'll show like all of it that shows and talks about and all that, just in case if you're curious and you want to see what exactly and how exactly, but that's generally how it goes. So let's say if a tree graph has a center vertex, bam, and doesn't have any non-trivial isomorphism, then the distinguishing number would be 2. That's also 2 if it's also, or if there's the center is a edge and there's at most one non-trivial automorphism. Okay. And now I'm just going to go down to some miscellaneous graphs that someone like that we've seen in class, like something like this. And in the paper that I'm going to get to in the references, it explains deeply on like how this was discovered to be a distinguishing number of 3. And for hypercube, I wasn't able to find the references for the hypercube, but it showed it in Wikipedia. So I just used that as an example for miscellaneous graphs. And just a simple star graph would have 5 because these all have to be different colors, each one of these vertexes or vertices, because if they were all the same color, there's no way to distinguish one from another. They would all just look the same. So each one has to be different. But for the center vertex, it could be any of the colors because it's the only vertex with 5 edges coming out of it, while every other vertex only has 1 edge coming out of it. Alrighty. And going down to the references, this one right here, this is the main paper that had everything that was talked about. So I was talking about the tree graph where I was referencing, oh, if you want to look more into it, look into this paper. This is all it. And then this is how I was able to find the Peterson graph, the answer for the Peterson graph, and all that. Another helpful video, a video that I actually found on YouTube was a Zoom recorded video. And I think it's for like another college's seminar or something like that. But it basically talks about distinguishing coloring and determining the sets for Michaelistanian graphs. I'm not sure how to say that name, but I didn't really care about this second part of the video. I only cared really about the first part, which was talking about distinguishing coloring. And it kind of just helped me get a basis of like what distinguishing coloring is in general. And I only used the first 13 minutes of the video anyways. And my last source is Wikipedia. All right.